Hello, my name is Will Sedo. I'm a junior at St. Paul Academy, and this year I have been researching the algae Didymosphenia geminata. Commonly known as didymo, this diatom algae is commonly found in cool, fast, and oligotrophic waters. The living portion is contained to a relatively small number of cells, like the one on the right, and most of what you see are the dead carbohydrate and phosphorus-rich stalks which contribute to its other name, rock snot. Didymo is distinguished from similar diatoms in part by how it is able to connect enough nutrients from oligotrophic water to produce a layer of stock material covering an entire riverbed over a decimeter thick for miles. In the past 30 years or so, Didymo has become a nuisance species across much of the world. Its historical range is contained within North America and Europe, but it has also spread as far as Chile, Argentina, and even New Zealand. It negatively affects natural cycles and human enjoyment of the streams it inhabits, as its blooms are able to physically block recreation. But even a smaller amount of the algae's snot-like appearance has been reported to local water treatment plants as a potential sewage leak. Its impacts are already beginning to be seen in nature-based tourism industries like fly fishing, and many governmental bodies have begun treating it as an invasive species. Researchers also hypothesize that a change in environmental conditions has been leading to an increased density in the rivers Didymo already inhabits, further exacerbating this Didymo issue. Mitigation strategies for this diatom are currently under research, but many variables have proven really hard to study as Didymo has not yet been successfully grown in a lab. Kujuk et al. 2014 did have some success culturing individual cells in a 96-cell plate as seen on the right, but did not attempt to promote any stock production. I wanted to identify with as much certainty as possible the necessary conditions for the growth of Didymo. I identified the 8 variables which seem most relevant from my background research, looked at more literature to see what had been concluded so far, and then took a deep dive into the raw data from these studies and from records of USGS river monitoring points across the country. In all, I ended up consulting over 30 datasets and research studies, with more than 200 total data collection sites represented. The process differed slightly for each variable, but I generally tried to identify the patterns I found in the data and literature, and then verify those with more data. Here's what I concluded, starting with the 4 physical conditions. Substrate. The general profile of a Didymo-infested water body describes a simple rocky substrate, like pebbles or cobbles. In an interesting study, West et al. 2020 found that Didymo cells would return to rocks they had been scraped off of by researchers, but would not bloom as commonly as on rocks Didymo had previously colonized itself. Other studies have been able to successfully grow Didymo on foreign substrates such as porcelain tiles, suggesting another variable may have been at play in the West study, but the safest option for creating an artificial substrate would be to use rocks from where the Didymo sample is collected. Integral to stock building is sunlight, or more specifically, photosynthetically active radiation. This was very difficult to find numerical data on, as what light actually penetrates to the cell is dependent on numerous site-specific details. An assortment of studies from Kilroy, Bothwell, and their collaborators have shown that Didymo blooms, stock production, cell attachment, and cell length are all favored under higher light. Similarly, James et al. 2014 found an inverse relationship between tree canopy cover and Didymo coverage, and my own analysis of their data showed that the most successful growth sites all fell within the range of 5 to 15% tree coverage. Any artificial light source used must also contain ultraviolet radiation, as studies have found that similar stalked diatom algae grow in 2 to 4 times greater abundance under UVR. Further research into the absolutely fascinating potential hypothesis that the recent global increase in UVR has influenced the recent global increase in Didymo as described in James et al. 2014 is warranted, but again is research most possible in a lab. Didymo cells have been collected from a range of temperatures, but are found most in cold water. This may be because of a true preference, or could simply be that colder water temperatures commonly correlate to other necessary criteria. Again, this isn't something we can easily study in the field. For my data analysis, the species is generally found in a summer water temperature of around 15 degrees Celsius. A Didymo colony located on the Kootenai River in Montana shows a temperature pattern that follows a basic annual cycle, reaching its coldest around 0 degrees Celsius in late May and rebounding to around 15 degrees in early September. Cell growth will continue even in the winter, but no research has yet been done into what temperature cycle does to Didymo and what the implications of a warming climate may be for the species' continued expansion. I was unable to find any numerical data for water velocity, but all available research describes Didymo as preferring fast-moving, turbulent water with relatively constant flow, such as below dams. Spalding and LL 2007 found that the single best hydrological predictor of Didymo biomass was the number of days since a significant flood, as once a Didymo colony is established, there are few natural ways for it to decrease in size. Water speed is something that may have to be adjusted some in lab to perfect. Out of all the variables I studied, phosphorus is perhaps the single most researched. It is central to what scientists have deemed the quote-unquote Didymo paradox. Didymo stocks are made from soluble reactive phosphorus, or orthophosphates, yet phosphorus concentration is negatively correlated to Didymo presence. In their extensive literature and field study of Didymo and orthophosphates, West and all 2020 found that the common threshold for growth was very low. In South America, around 4 micrograms of orthophosphate per liter. In New Zealand, around 3. And in the American Rockies, rarely above 2. Kilroy and Larned 2016 identified a potential threshold of around 2 micrograms orthophosphate per liter, a threshold that appears again in Coons et al. 2018 and James et al. 2015. A suggested value of 2 micrograms seems reasonable, but this is likely a variable that will be manipulated frequently in any research. In an in situ study, Bothwell and Kilroy 2011 found that nitrogen was not a primary limiting nutrient in Didymo growth, and similarly in 2014 found that nitrogen increased up to 115 milligrams per liter did not improve or even affect cell attachment, but did eventually correlate with a shorter stalk length. Another study used fertilizer to increase nitrogen concentrations, and with concentrations as high as 250 and as low as 10 milligrams per liter, discovered no detectable effect on the Didymo population. A proposed threshold of 10 milligrams per liter has been suggested, below which cell division and development is limited, but above which growth seems to continue largely unimpeded. Every applicable measurement I found had nitrogen values that fell within this proposed range of 10 to 100 milligrams, with most clustering around 40 to 50. Iron levels, the focus of multiple papers, has at times become controversial over the effect it truly has on Didymo. It was first hypothesized in Sundareshwar et al. 2011 that Didymo growth was in part predicated on the availability of highly reactive iron, and they experimentally found that more iron allowed dead Didymo stocks to collect more phosphorus. The result in livestock was not quite as impressive, and disputed in studies like Bothwell et al. 2012, who found from a literature and field-based approach that Didymo occurs best in low iron water. This was mirrored in James et al. 2014, who found iron levels to be inversely related to Didymo bloom size in 39 sites along one river. The median iron values for locations with confirmed blooms in one study ranged from 0.05 to 0.2 milligrams of iron per liter, but clustered around 0.08 milligrams. Out of 7 studies and databases I analyzed, the data from 6 fell within this projected range. Didymo has been recorded in a variety of pH values, from as low as 6.7 to as high as 9.62. A lot of variation within this range exists, but for example in Koweka and Senecki 2003, a pH range of 8.1 to 8.3 was recorded during the most prolific summer months of growth. This table represents a summarization of the results I detailed in the previous slides. Although many questions remain as to which of these factors actually determine the success of Didymo, all available data and research seems to agree on this relatively narrow window for the best growth. The next significant step in this research would be actually trying out these conditions to verify that they do in fact work. This is a project I'm hoping to be able to take on this spring, assuming I'm able to find a specimen of Didymo to work from. A proposed setup will include a long, wide, deep, artificial riverbed in a style similar to this wave tank, and cobbles and water collected from the same river as the Didymo sample. Conditions would be checked frequently to verify nutrient levels, and water could be rapidly recirculated throughout this tank to maintain speed. If physical testing was successful, possibilities stemming from the ability to test ideas in an isolated environment are endless. After learning more about Didymo in a laboratory environment, we can begin looking at things like the Didymo paradox, and whether as humans we may be able to apply some of the same techniques Didymo does for removing nutrients from water. In one possible example, there may be an application for the strategy Didymo uses to remove phosphorus from rivers, to help us clean phosphorus from water dangerously impacted by phosphorus-based fertilizer. In many ways, the possibilities here are endless, as we don't yet know what information can be learned. But I hope in some way my work has been able to propel us towards that possibility. And here are my resources. Thank you so much for listening to my project.